For this circuit that is given here, this op-amp circuit, we want to find the following: what the ideal gain is if op-amp 1 is used. So you're given different op-amp parameters. And so the values for the different op-amps are seen here. So these are the parameters for amp 1, these are the parameters for amp 2, and these are the parameters for amp 3. So in this part of the problem, it asked for amp 1 values, and it said, what is the bandwidth of the circuit considering both the unity gain and the slew rate for a given input? And then it wants to know the maximum and minimum values when you consider input offset voltage. And then lastly, how to modify the circuit to minimize the effect of the input bias current. I'll talk about these in a little bit. So the first question asks for the ideal gain of the circuit. So you look at where this input is coming into and you see it's into the negative. So this means it's an inverting amp, which the equation for that describes it as this value over this combined value, which is 500. And then you get them negative. So the ideal gain for this one is a minus 18 volt per volt. The next part of this question asked that if amp 1 value is used, what is the bandwidth of the circuit? And you have to consider both the unity gain bandwidth and the slew rate. So we have two values for that. So the slew rate for amp 1, which is what we want, we're going to consider both of these. We want to consider the worst case, and in that, the first one we're going to do is the frequency related to the unity gains. So remember that f of c, which is the max frequency or the critical frequency, is f of t, which is the unity gain bandwidth, over inverting gain. So remember that it's inverting. So the f of max due to the unity gain frequency, f of t, is f of c is equal to ft over the non-inverting gain. And in this case, the ideal gain was 18, but we want the non-ideal gain, which is 1 plus the 18s, for a value of 19. That gives us this frequency, 526,316 hertz. We also need to consider f max due to the slew rate. So this is the slew rate divided by either peak to peak or 2 times peak of the output times pi. So this is the output value, so make sure you use output here. And remember slew rate, so we're going to look at the slew rate, and there's two values for the slew rate. The lower value is going to mean a lower frequency, and so that is going to be the worst case value. So we want to pick that one. So 0.05, and we got to remember it's in microseconds, so we have to include that 1 over 1 times 10 to the minus 6. The output is 0.1 times 18, which is the gain, times 2 pi, and it gives us a value of 4,421 hertz. Now we notice that this one is a lot less, so this will be our limiting bandwidth, and we say that is the bandwidth of the circuit. So the output of this again is given because the input times the gain is your output. So this is your input times your gain, and in this case it's an inverting configuration, so it'll be times that 18. So this is your input. So part C is if amp 2 amplifier is used and your input is Vn is 0.1 sine omega t, what is the maximum value seen at the output considering only the input offset voltage? So for amp 2, we're going to look at the input offset voltages, and again we see we have two values, and the worst case in this case is going to be the higher value, meaning it has more of an offset, which is not what we want. The ideal would be no offset, 0 offset. So 4 millivolts is the value we're going to use to determine the input offset voltage effect. So the input without the offset is going to be a 0.1, which is the value of the amplitude, times the gain portion, which is 18, or minus 18 was actually from that. And then we have the offset, and remember you also have to use the non-inverting gain here. So this gives us 76 and then a plus or minus 1.8. So 76 plus or minus 1.8 sign gives you this max and this min value. The last part of this problem asks for you to modify the circuit and consider the input offset correct. So in that case, we need to match the resistance at this node and the resistance at this node to be the same. The resistance at this node, if I combine these two, I have a path there to ground, and I have a pathway here to ground. And the ground comes from the input being grounded. Remember, any independent sources become ground, or become short. In this case, it was connected to ground, so it becomes a short to ground here. And also the output acts like a voltage source, so we actually are able to ground that on this side too. So we have 9K in parallel with 500K, and that gives us a value of this, but then we have the 100 ohms also connected in there, so we have to subtract off the 100, so that's where this minus 100 comes from. So we will put in a value of 374 as a new resistor in series with the 100. This concludes this solution. Thanks for watching.